Hi everyone, and welcome to PyDataMCR for our July event. We're joined today by two fantastic speakers, so it should be a very interesting event. If you want to get involved, you can do. Tweet to us at PyDataMCR on the Twitters. Get involved at the PyData UK Slack in the general or Manchester channel. I can't remember. Get involved there. You'll find out. It'll be all the rage in all the conversation and all the channels, I'm sure. The more questions, the better. PyDataMCR is brought to you today by Joe Allen, who's doing the streaming, John Carney, myself, who's hosting, and Jennifer Stark and Sean Hyde are both handling questions in YouTube, comments, Twitter, and Slack. So yeah, if you've got any issues, whether it be around code of conduct or anything else, ping any one of us and we'll try and get it sorted as soon as possible. Speaking of the code of conduct, PyData is dedicated to providing a harassment-free meeting experience for everyone. As part of this, it's really important to remember PyDataMCR is a professional event, so behave professionally. If you've got any issues, we've got the anonymous support form, or again, get in contact with any of the volunteers. So upcoming events, we've got our code night on August 5th, so that will be next Wednesday. Don't forget about it. We've still got an August events coming up, which is probably going to be around data ethics. So we're still figuring out a date for that, but stay tuned. Again, unfortunately, we've not got around to sorting it out this week, but keep your eyes peeled for Python Northwest events, Open Data Manchester, Herplus Data, and all of our friends who I've probably missed out. Because, yeah, a lot of good Manchester data events still going on. Speaking of which, we've got our podcasts, which have recently been released. Hera Hussein from Open Contracting, Adam Fletcher from Equal Experts, and Eslin Bikomo, who's focused on data engineering at Agent Software, I think. Oh, maybe misremembered. If you've got any announcements, if you're looking for a job, if you have a job and you're looking for someone to fill it, get involved in the Slack, in the jobs channel. And again, if you organize a meetup, pop it in the Slack channel and I'll make sure I shout it out before the end of the event. So if you want to get involved, whether in the future, whether it's as a speaker, as a podcast guest, as a sponsor, or getting involved in the response team, then again, get involved on Twitter, on the meetup, or after the event. So on to tonight's event, we've got two speakers, Dr. Stephanie Hyland from the Microsoft Research Group, Cambridge, and Reka Solymosi, a lecturer in Quantitative Methods at the University of Manchester. So we're going to start off with Stephanie first. So over to you, Stephanie.
Am I visible? Great.
Welcome.
Great. Thanks for the introduction, John. I'm very happy to speak. So let me just try and successfully share my slides, which is always exciting despite having done it before. Let's see. Okay, this looks pretty promising. Does that look good?
There we are. Perfect.
Okay, great. Okay, so today I'm going to be talking about some of the research that I've been doing. Okay, there we go. Some of the research I've been doing in Cambridge, Microsoft Research, and just to note that everything I'm talking about here is a collaboration with another researcher, Shruti Topal from our confidential computing group. So very briefly about me, I'm a researcher in the healthcare intelligence team at MSR Cambridge. So normally most of my research focuses on machine learning for healthcare. My slides are possessed apparently. But today I'm going to be talking about privacy preserving machine learning. Yeah, if you have any questions, you can get me on Twitter or you can email me. Okay, so just to give a bit of context on why we're thinking about privacy preserving machine learning, let me walk through the kind of scenario. Okay, PowerPoint is doing something really weird. Okay, so as I mentioned, I think about machine learning for healthcare. So we think about a scenario where a hospital may want to train a machine learning model on their sensitive in-house data. So this could be the medical records of their own patients or something similar. So they want to be able to develop a model, maybe it's predicting or diagnosing COVID from X-ray scans or something, and then they want to be able to share it with the world. So, oh my god, what's going on with my slides? Okay. So okay, one sec, let me just fix this real quick. Sorry.
Hey, don't worry about it. Take your time.
I had, there we go. Yeah, I had this problem before. You would think that since I work at Microsoft, I would know how to use PowerPoint, but that's not one of the requirements for the job, as it turns out.
People forget how in depth these things are. You don't know until you need them.
Yeah, so this happened to me before. PowerPoint will do this thing where if you've practiced your slideshow, it will store the timings per slide, and then it will automatically play them for you when you least expect it. So hopefully that's not going to happen now. Let's see what happens. Okay, so hospital develops a model in-house, assuming this is all secure. They have, you know, whatever protections they need, that they don't assume any adversary is going to get into their training procedure. But then they want to share this entire machine learning model with the world. So this is not an entirely unreasonable thing that they might want to do. They could say, you know, we've built this really high-performing classification model. We think it's really helpful. We want to give it to other people so they can use it. The problem is, I'm not going to go too deep into the specifics of this, but there have been various attacks demonstrated on machine learning models that you can learn things about the training data from the model itself. So examples like you can kind of create almost images of the faces of the people if it were, you know, a facial recognition data set, for example, that you can sort of reverse engineer these models to get information about the training data. And in this scenario, the data is sensitive and it's ethically and also legally inappropriate to leak that information. So the question would be, how can they share their model in a way which gets the utility benefits of other hospitals being able to make use of it without risking the private information of the people whose data may have been used to train the model? So this is the, think of this as the setting that we're working in. So this work is really all about a type of privacy called differential privacy and the optimization method, stochastic gradient descent. So I'm going to explain both of these. If there are more questions, I'm happy to go into more detail. Hopefully everyone will have the level needed to understand the rest of the talk after this. And if you already know this, then you can zone out for a little bit. So we're thinking about stochastic gradient descent, or SGD. SGD is the optimization method which we use to train neural networks, deep learning, or technically some variant of SGD, but the basic idea is the same. So the idea of gradient-based optimization, as this little animation is showing, is that we're trying to find the minimum of some function, and we do this by taking little steps in the direction of the negative gradient. The way SGD is different to a traditional gradient descent method is that it follows a noisy version of the gradient. So this is typically because your data set might be absolutely enormous, and computing the full gradient across the entire data set is really computationally infeasible. So what you do in practice, and this is not only computationally reasonable, but actually provides some other theoretical benefits, is you take samples of your data. So these are mini batches of size, usually 32. And then you estimate your gradient on that batch of data. What this does is it introduces noise into that estimate. So what I've shown here is you can see this sort of nice shape, and there's, you know, you're taking gradient steps. In SGD, there's always a chance that you might kind of change direction. The ground, your estimate of where the gradient is could be wrong. There's a little bit of noise, so your path won't be quite as smooth. So that's SGD. Everyone is now an expert in deep learning because that's basically what you need. So differential privacy. Differential privacy is a slightly initially unintuitive or maybe confusing notion of privacy, but which is actually really powerful. So the basic idea of differential privacy is around ultimately protecting whether or not someone is in a data set. So on a high level, the idea would be that a query, so think about a database, you know, you can either be in it or not in it. The query on that database is differentially private if that query is not going to change very much if one of the entries in the database is there or not there. And it could be any of the entries in the database. So to give an example of something which would not be very differentially private, if I want to compute, for example, the average income in an area, if Jeff Bezos is in my data set, this average estimate is going to be really, really large. And if he's not in the data set, it's going to be a little bit more normal. So that means that the output of this, what's the average income, is going to change massively just because people like Jeff Bezos exist who could either be or not be in the data set. So differential privacy is really around this idea of small perturbations to your data set or your database should not really affect the query that much. And you can quantify this mathematically by saying, if the query defines some probability distribution, then when I change my underlying data set a little bit, that probability distribution should not change very much. And the amount that it's allowed to change is bounded by a parameter called epsilon, which I will talk about a lot. But the thing you need to know about epsilon is allowing you to quantify the level of privacy. The bigger epsilon is, the less privacy you have. So epsilon is kind of like the privacy loss. So you ideally want epsilon to be really, really small. That means these distributions are not changing very much, even when you change something in the underlying data. So one of the things that we think about is, well, how do I make a query differentially private? Because this is a notion of privacy which is very powerful. It means that your adversary can't figure out whether or not someone is in a data set. So as I mentioned, we think about this query as having some probability distribution, which means it needs to be probabilistic. And then it needs to satisfy this mathematical statement. So what you can do, so in the example of the average, for example, computing an average is not a probabilistic thing. There's a sort of deterministic answer. So one way you can take a sort of deterministic function like the average and make it probabilistic is by adding noise. And one of the ways to do this is called the Gaussian mechanism, which is basically you take some deterministic function f, which could be compute the average, and then you add some Gaussian distributed noise with zero mean and some variance which is chosen to give the level of privacy that you want. And that level of privacy is essentially, there's theory for this, which will tell you, okay, what is that sigma value? What does that need to be to achieve a certain level of differential privacy? So this epsilon parameter, as I mentioned, is the privacy parameter. There's also a delta parameter, which also quantifies the level of privacy. So given epsilon and delta, you plug it into this formula, which the form of which doesn't matter too much. Just remember that there is a formula. And then you can say, okay, this is how much noise I need to add. One of the important inputs into this formula is called the sensitivity of the function. So in the case of computing the average, the sensitivity of the average is the biggest change that this function value could have when you change the data set by 1. So in the case of an average, if someone has potentially unbounded income, or in case of computing the average income, if the income could be completely unbounded, then the L2 sensitivity is also completely unbounded. If you're thinking about, I want to compute the average height of people in this data set, and we say, okay, it's impossible for someone to be taller than, I don't know, 3 meters tall, then the sensitivity of the function is going to be something like 3 meters. It's going to be sort of the worst case change in the function's output. So you see that the more sensitive the function is, so the larger its L2 sensitivity, the more noise you need to add to obscure the change due to the change in the data set. Okay, so hopefully everyone's an expert on differential privacy now. So what does this have to do with machine learning? So remember that what we're trying to do is we're going to train a model, and then we're going to release it to the world. So what we can do is we can think of the training algorithm, SGD, as a function on the data. So we apply our function f, SGD, to our data set, and the outcome of this is a set of weights. We can estimate the sensitivity of our training function by thinking about what's the biggest change in the weights that I can get when I change my data. And then using the Gaussian mechanism, I can add noise to make SGD differentially private. So this was the first idea that we had in this project, and we were really excited about it. And then we realized that someone published it like 3 years before we had even started thinking about it, which is always kind of reassuring, but sometimes frustrating to realize someone's already done your idea. But it's fine, because it means that we can start thinking about the next thing. So one of the drawbacks of what I just described is that when I mentioned the Gaussian mechanism. This is in the context of a deterministic function, something like computing an average. But SGD is not a deterministic function. If you recall, SGD involves noise. We sample random batches of data, which means that I can run SGD twice and get different answers. And this is something which machine learning practitioners are quite aware of. So we know that when you change the random seed, this changes your model initialization, and it changes the order in which you go through the data. So what I've shown here on the right is 3 different random seeds, 2 weights of a model, initialized identically, but then due to the random sampling of batches during training, you can see that these weights evolve differently throughout training. And that means that you could end up with different models simply because you changed the random seed. So what this means is that we should actually think about SGD not as a deterministic query, but as a probabilistic query. So when I run SGD on my data, I'm basically getting a sample from some distribution over weights. So the theoretical question we would ask then is, what is this privacy parameter epsilon of that distribution? Assuming the adversary doesn't know what the random seed is, which is a reasonable assumption. The problem is we don't actually know what this distribution is. So my drawings here are like, oh, it's a normal distribution, it's normal. But we don't have a theoretical argument or a sufficient theory right now to say that it is normally distributed. I have a couple of citations on this slide, which maybe people can like pause the video and check it afterwards. This is like an active area of research. There's a lot of really exciting theoretical machine learning research going on in this direction to try and characterize even what does the noise in the SGD gradients look like, and then figuring out how this relates to the final distribution over weights. This is let's say, ongoing work, future work. So what we did, and what I'm going to describe in the rest of this talk, is we approached it empirically, which is exciting because this is PyData, so I can talk about data. So before we run our empirical study, we want to know what questions we actually want to answer. We're going to run a lot of experiments, so we need to make sure we're collecting the right data. So we kind of focused in on 3 main questions. So the first question is to understand what's more important when it comes to the final model. Is it changes in the data or changes in the seed? So I've shown that we change the seed, we can see the weights change. Intuitively, changing the data should probably change the outcome of the model a little bit. So we want to quantify which one of these has more of an impact. The second question is, okay, we don't have a theoretical understanding of what this distribution of the weights due to SGD looks like, but maybe we can try and empirically quantify it and compute what is its variance. And we can then use what we know about differential privacy to try and relate that to a sort of intrinsic privacy that you would get from SGD. And then the final point is really, how would this impact the performance of a private model? Because the challenge with adding noise to the weights when we release the model is that typically it makes your model work worse. And in a healthcare setting, you really don't want that to happen. So we're really interested to see, could we possibly use some of what we've explored here to help improve the performance of the private model? So we ran a lot of experiments. The way we did this was we're focusing on binary classification. It's very simplistic. And we essentially run a grid where we either vary the data set or the random seed. So varying the random seed is pretty simple. You just make sure you've set all your random seeds appropriately, and you just vary this. When we vary the data, so remember that differential privacy is all about comparing 2 data sets which either do or do not have a given record in them, or a different training example. So what we do is we create a whole set of all neighboring training data sets where we've basically replaced one of the entries in the data set with some other value. And this is, so these data sets are almost largely identical, but they differ in one row. And this is what we need for differential privacy, or to compute differential privacy. So we consider 4 data sets, all very kind of traditional machine learning data sets. We're looking at MNIST, CIFAR10, and two data sets that are used often in the privacy world. This adult, which is about predicting someone's income, and forest, which is about classifying whether or not what type of forest something is. Note that we've turned MNIST and CIFAR into binary classification tasks. So I think it's 3 versus 5, and like birds versus planes or something. We've just taken 2 of the classes. And then in terms of models, we think about logistic regression, which is always a very classic baseline. This is nice because it's convex, or the loss is convex, which means we can use some existing theory. And then we think about small neural networks. So a kind of caveat here is that if your model has a large number of parameters, if you try and release this to the world, you need to add a lot of noise, and you almost completely destroy your model performance. So as of now, we're still thinking about quite small models, something like less than 1,000 parameters in them. And those are non-convex, which is also nice. Okay, so we ran a whole load of experiments. So it was about 10,000 a grid, which is about 100 by 100 of 100 dataset variants, 100 seed variants. We look for every dataset, logistic regression, neural networks. I included the size of the folders, but that doesn't mean very much because they're just text files. And then lots of other stuff in the meantime. So this is a kind of big-ish data problem. And I also thought, because this is PyData, I should mention a little bit about the implementation details. So this is my only slide on this, so if anyone has more questions, I'd be very happy to discuss. I wrote all of this code myself, so I know the intricacies of it. So what's interesting here is that this is machine learning, but most of what we're doing in this project is not actually training models. So we train a model, of course, we train loads of models, but that's really a tiny piece of it. A lot of what it's about is really, okay, now we've trained all these models, we can see all of the evolution of their weights throughout training. We need to start computing these quantities like the variance and the privacy parameters and so on. So most of the work is actually in pandas because it's a lot of just data processing and comparing and computing statistics and so on, which is awesome. Okay, so I've described the setup. I'll talk a little bit about some of the results now. So our first question was, what's more important? Is it the data or the seed? So what I've shown here is for a certain model class on CFAR. This is a distribution of the Euclidean distance between pairs of models. So if you imagine I take my model, this is actually logistic regression. So it has something like 50 coefficients, 50 weights. And then I compare these 50-dimensional vectors for model trained in scenario A and model trained in scenario B. And scenario A and B can differ basically in 3 ways. In the gold region, these are models where the random seed was the same, but the underlying data set differed in one example. In green, we have the data set was completely fixed, so it's exactly identical data, but the random seed changed. And we either consider the model has a fixed initialization, so that's in green, or the initialization of the model is also set by the seed in purple, which is the traditional machine learning scenario. The reason we separated these was partially because we wanted to see how the sort of purely the effect of going through the data in a different order would impact the results, which is what's in green. So what we see is basically, I think I have this in the next slide. The gold is much smaller than the purple, and I'll put it back here so it's easier to see. The gold bit is a lot smaller than the green and the purple, which means that if you're purely just comparing the Euclidean distance between model weights, changing the seed matters a lot more than changing the data, which is kind of just confirming the sort of suspicion that we already had, which is partially why we thought this project would be like worth pursuing at all. Because when you think about differential privacy, if you have more intrinsic variance due to factors like changing the random seed than due to changing the data, then you think you might have a chance of having some differential privacy. We can make another kind of interesting observation, which is that this dotted gold line is a theoretical bound on the sensitivity. So in the case of logistic regression, people have already tried to theoretically say what the dataset sensitivity should be, and that's what that gold line is. But from our empirical analysis, what we can see is that it's way bigger than the real observed sensitivity from our experiments, which suggests that the theory needs some more refinement so it can have a more realistic bound. Yeah. And then, yeah, so we have 4 data sets and 2 different model classes for each. So we see largely the same story in all cases. For neural networks on the bottom, there's no theoretical bound, so we can't say how tight that is. And you see maybe a little bit more of a long tail, but qualitatively we're seeing pretty much a similar story with some interesting variations that we haven't yet explained. So the second question is around the intrinsic variance. So this is a question of, okay, if SGD is sampling from some distribution over weights, what is that distribution? So we make a really big simplification here, which is that we basically assume that the form of that distribution is Gaussian, and then we want to just compute its standard deviation. So I've shown on the left, this is the joint distribution between two random weights. And it looks kind of independent, which is sort of supporting what we did here. But this is a big assumption. And if this makes you really angry and you're like, oh my God, that's definitely not the case, please get in contact with me. We'd love to loosen this assumption, but it becomes rather tricky if we do that. Okay. So in doing so, we're able to compute this standard deviation of the distribution of weights. So I'm going to show basically the same table for a couple of slides and walk you through the different numbers here because there's a bunch of numbers. So if we think purely about the standard deviation of the weight distribution, what we have is we compute this number for each of our 4 data sets for both logistic regression and neural networks. These are numbers that we can compute. They don't mean all that much on their own. We can kind of look at them and be like, oh, it's interesting that they're kind of similar in the different data sets, but they're different for the neural networks and so on. We don't have a theory to explain these differences yet. This is all very phenomenological. What we can then do is say, okay, well, this is the noise. How does this relate to the sensitivity? Because that's what's going to get us to this notion of privacy. So we can also compute the sensitivity. So remember, the sensitivity is just how much the output of the model changes when you change the data. And we can read it off the plots that I already showed, where we compute the difference in model weights. So what we have is 2 sensitivities here for the logistic regression. One of them is the theoretical one, that gold dotted line, which was very loose, was very higher than the empirical one. And then we also have the empirical sensitivity. So for example, if you look at CFAR, you see the theoretical sensitivity, that's without the star, is way bigger than the empirical sensitivity. That's because the theory is a bit loose. But yeah, so then we can compute our sensitivity. And then in order to get some notion of privacy, we basically need to use this equation for the Gaussian mechanism, rearrange it a little bit to try and solve for epsilon as a function of the sensitivity, which is this delta F and sigma. And if we do that, we then get what we're calling the sort of intrinsic epsilon. And in the case of logistic regression, there's 2 variants depending on whether or not you use the theoretical or the empirical sensitivity. Cool. So what we have here is a bunch of numbers. Now, remember that I said smaller epsilon is better. There's a kind of ongoing discussion in the privacy community as to what a good epsilon is. But one of the rules of thumb is sort of like less than 1 is good. Bigger than 1 is pretty bad. So what we see is that the closest we get to 1 is for the forest dataset, which is the biggest dataset, and it's about 1.25. So if you had if you were at risk of coming away from this talk thinking, oh my God, SGD gives privacy, I can just train my deep models on whatever dataset I want and then release a model to the world and it's fine, don't do that, please don't do that. It doesn't give you enough privacy, at least not according to these computations so far. But it gives us something. For neural networks, very, very bad values. But at least for logistic regression, epsilon of 1 or 2, it's not good enough on its own, but it might be good enough to use with a little bit more noise to do better in model performance, which is what we're going to do next. So we compare the performance of 3 different settings. The first one is a sort of like gold standard best model you could get, which is you add no noise. So it's not private, you shouldn't release it, but this is sort of the best your model is going to do. And then we consider 2 variants. One of them is where you just add noise, ignoring that SGD has this intrinsic randomness. So this is using this paper that I mentioned. And then the second one is where you add noise, accounting for the randomness already in SGD. So the idea would be the Gaussian mechanism tells me this is how much noise you need, but then I say, but SGD already has a little bit of noise. So I'm going to add a little bit less noise, and then I'm hopefully going to do better. And then we can also compute using the theoretical or the empirical sensitivity as before. So here's another table of numbers. So what we have is we compute our noises performance for 4 different data sets. This is our best performing model. This is logistic regression, so it's not entirely surprising that we're only getting 95% accuracy on MNIST. These are accuracy numbers. And then we look at the performance of the noisy model, assuming SGD is deterministic. And we see across the board it drops. In fact, for the adult data set, you're dropping to almost terrible performance. 53% accuracy is a huge drop. And then what we show is how much of an improvement you get when you use the fact that SGD already has some randomness in it. So what we're seeing is pretty small absolute numbers, and that's partially because this intrinsic epsilon is relatively large. It doesn't have that much intrinsic noise in it. But in some cases, like in forest, which is sort of our best scenario, we do see that it closes the gap. And then we repeat the same, closes the gap a little bit. And then we repeat the same thing using the empirical sensitivity. In this case, the models are just performing better because you have to add less noise because you're not unnecessarily overestimating it. But you see a sort of similar situation. And we run paired t-tests to test the statistical significance of this. So these are very small but statistically significant improvements. Okay, so that's my spiel. I'm just going to summarize it because I realize I've been talking a lot, probably a little bit quickly. So the point of all of this is that people have not really thought about the fact that SGD or other learning algorithms have randomness in them when building their private models. They tend to think a lot about adding additional noise, but they haven't, at least to my knowledge and everyone who's been involved in this project, we have not yet found anyone who's tried to actually use this stochasticity for the purpose of privacy. So while the theory kind of piece needs to be assembled and it poses some really big challenges, we've done a large-scale empirical study to demonstrate that yes, the seed does have a bigger impact than small dataset perturbations. We see that we can get an intrinsic epsilon, or that there is an intrinsic epsilon between a kind of surprisingly good value and a really terrible value, depending on the model and the dataset. And that we've also shown that when you account for this intrinsic noise, you can get a statistically significant, if small, improvement in model performance. So it's something that we should think about. And if we could engineer SGD, for example, to exhibit more noise in a way that doesn't prevent its optimization performance, we could also potentially do better here. So as I mentioned, we have loads more questions. So if you are interested in collaborating, please email me, stephanie.hyland@microsoft.com, or tweet at me, which is how John got me, because we have loads more questions. So just to give an example of some of the things that I'm excited about, the first thing, we know the weights aren't really Gaussian distributed. So what are they? We have a lot of data, and we really want to look at it to try and figure out what do these distributions really look like. The second thing is we saw that there's variability in our findings across datasets and models. So what is it about these datasets that makes them different? And we reasonably expect the models to perform differently, but maybe even within the same class of models like neural networks, what kind of variability would you expect to see there? The third thing is that this has all been for sort of vanilla SGD, fixed learning rate, nothing fancy like ADAM or RMS prop. So does this still hold if you use the types of SGD variants that are commonplace in practice? And then, as I mentioned, could we engineer SGD to actually enhance the variability without hurting performance? And many, many more theoretical questions about SGD and optimization. So with that, thank you very much. You can tweet at me or email me, and you can also read the preprint for this work on arXiv. And with that, I understand there may be the potential for questions. I'd be very happy to take them.
Yeah, thank you, Stephanie. That was really fascinating. A huge amount of information, but like really, really interesting. Thank you. So we do have a couple of questions. Yeah, again, feel free to add them to the YouTube. Sean and Jennifer will be checking them out and relaying them. But kind of starting off, from a more fundamental perspective, you mentioned about all this work looks at differential privacy. What other kinds of privacy are there?
Oh, that's an interesting question. So there's
a lot, but you don't need to go into too much detail.
yeah. Let me see. Okay, so I'm not enough of a privacy expert to give you the kind of categorization of different types of privacy. But I can tell you maybe why differential privacy is so exciting for people in the data space. So differential privacy is basically very powerful partially because it thinks about databases and people's involvement in databases, which is sort of the scenario that people think about a lot. So differential privacy is about promising if you participate in this database, nothing worse will happen to you than if you had not participated, if that makes sense. So it may not be entirely clear how the definition actually relates to that notion of privacy, and it's a little like to that promise. It's a little bit takes a little bit of time to get your head around that. And if you're interested in learning more about differential privacy, you should check out Frank McSherry's blog, and or the book that he wrote with Cynthia Dwork, The Algorithmic Foundations of Differential Privacy, where they talk a lot more about the kind of the theory and so on here. I think this, yeah.
Can you repeat that name?
Yeah, Frank McSherry.
Right, Frank McSherry.
Yeah. Or Cynthia Dwork. Yeah, so they're great resources for more about differential privacy. I think also what's really powerful about differential privacy is that it's not binary. So it's not like you either have privacy or you don't have privacy. It allows for this notion of this epsilon value, which is sort of, you have a kind of some level of tolerated risk, for example, which you can set depending on your use case.
Sure. I mean, generally, I feel like in security, it's never a black and white, binary good bad situation. It's shades of grey.
Yeah, for sure.
So down that road of ethical stuff, kind of thinking in terms of the use case you've mentioned in a hospital, in a situation where the model can save lives, there's a trade-off there between model performance, making it publicly accessible, and maintaining privacy. I don't have I'm not sure exactly what the question would be, but how do you make that trade-off? Because there's a bunch of really important factors at play there.
Yeah, for sure. And I think this is something which maybe there's a very topical version of this, which is around COVID and track and trace, and the tension between the sort of the greater good of public health or of individual health, saving lives, versus the abstract notion of privacy and civil liberties and so on. And so it is a genuinely difficult question. There's a kind of easy kind of get out of jail answer to this, which is that when it comes to using people's data, there are laws, and you kind of you want to abide by the laws. GDPR, and in the US there's HIPAA and so on, which very strictly tells you how you can work with medical data. If I had to give my personal, not speaking as a representative of my employer, kind of feeling here, it's that I think the abstract notion of privacy is important enough that we should not throw it away because we think that we'll be able to save more lives if we potentially misuse someone's data. I think especially when it comes to the use of machine learning in healthcare, there may be some model which is so incredibly groundbreaking that it seems unethical not to bring it to the world, and you really have to, but at least right now we're not there. And so for now, we definitely need to make sure that we are not abusing the privacy of the people who are involved in these data sets, because otherwise, if you say, oh, but my model's really great, I really want to bring it to the world, you're not going to be training any more models on anyone again, because you've disrespected the people who went into your data set.
That's a very good answer. Thank you. Very complicated question.
Yeah, it's a tricky topic.
Difficult to summarize in a minute.
Yeah.
So this is kind of one of my questions. I think it may be a stupid question, but I'm going to ask it anyway. You've talked about the differences in weights in terms of like Euclidean distance. Depending on the kind of the activation function you're looking at, would there be situations when it wouldn't be in a Euclidean space?
Yeah, that's not a silly question at all. It's a very good question. So this idea of what is the correct metric for comparing machine learning models is really interesting. I think in our case, the reason you look at Euclidean distance is actually a byproduct of the Gaussian mechanism. So when you're deriving essentially what epsilon and delta and sigma need to be for the Gaussian mechanism, you're looking at differences of Gaussians, and what ends up coming up is Euclidean distances. So it's a side effect of the fact that you're looking at, in our case, a multivariate normal distribution. But in general, yes, for sure, it doesn't necessarily make sense to look at the Euclidean distance of the weights of neural networks. And one scenario in which this kind of fails, interestingly, and I don't know how best to address it, is that you have a kind of invariance inside your neural network. So for example, if you think about, you have like multiple layers, you could reorder the weights. So long as I reorder, I flip these and then I flip all subsequent weights, my neural network will be kind of functionally the same. But if you were to like put out all of its weights into a single vector, they would have flipped in different positions. And so you have this kind of almost not a complete permutation invariance, but you have some invariance, which means that if you then try and compute the L2 distance between these different networks, they could look like they're very different when actually they're functionally completely identical. So this is something that we're not actually addressing right now, but for sure it kind of makes you think, yeah, that maybe this isn't the right metric. So yeah, really great question.
Does that come into, is that all about the assumption you made about it being about it being a Gaussian?
So for us, yes, it's to do with
Okay.
this Gaussian assumption. Yeah.
Cool. Thank you very much. Let me just check if there's any more questions. So one last question. Aside from healthcare, where else do you think this could be used?
Yeah, so for sure, privacy-preserving machine learning has loads of potential applications. I think there's anywhere where you have some private information that you want to keep private. So maybe less glamorous in healthcare, but financial models and so on. Maybe you don't want your competitor to steal your stock market model or something. I don't work in that. Those would be areas. I think in the specific case of what I'm talking about, it is really a scenario where you want to train your model and then be able to like really release it to the world. So a lot of the time people will do something where you're able to access outputs of the model. So for example, when I use Google Translate, I'm getting pairs of like inputs and outputs from Google's model, but they're not giving me the full model straight up. That's a slightly different scenario to what we're thinking about. We're thinking about really like, go take this model, do whatever you want with it. So another scenario could be, maybe in social sciences, if you're building some kind of any model which is using very sensitive information that you don't necessarily want to be shared. Like maybe you build it on census data and you think it's a really useful model for maybe city planning or something, but you need to protect that data.
Cool, that makes sense. Thank you very much, Stephanie. Really fascinating talk.
Thank you for the many questions. Yeah, as again, yeah, please email me or get me on Twitter if you're interested to discuss more. Thanks.
Thank you. Up next, we've got Reka Solymosi from the University of Manchester.
Hello.
Hey, Reka.
How's it going? All right, let me do the ritual dance of let me share my screen and share. Okay. So hopefully you can see my screen now.
There we go.
Yay, very good. All right. So thank you for inviting me to talk here. My talk is going to be about maps, so that's always fun. But I'm going to be talking about how even beautiful maps can be slightly very misleading, depending on the decisions that you make when creating these maps about the different steps in your spatial data visualization process, and how they might affect the legibility of your maps. So the takeaways that your readers or viewers of your maps will understand that you are trying to communicate. So I like to start off with a map so people know what I'm talking about. And this is a very relevant or current map, I guess, because it shows you COVID-19 infections or cases per 100,000 population. I think this is in the American state of Georgia. And so these are two different maps in two different time points. And there's a slight problem with the message that they're communicating. And I know this isn't an interactive session, so I can't say like, oh, discuss amongst yourselves and then report back. But while I'm talking, I just want to call you to look at the two maps and have a think about what might be wrong with the way that this information is being displayed, what might be misleading about the story that this map is trying to convey about the cases of COVID between these two time points. So if you have a look, they should look relatively similar, right? But actually, if we focus on the legend to do with the map, we might start to see a slightly different story than if we just looked at what is the visual that's coming out at us from the sort of first instance. And indeed, what this map isn't quite screaming at us is that within the span, I think there's 15 days between these two, but I'll just load the full tweet from where I borrowed this map. In the span of this 15 days, there was a 50% increase in cases, but this map really isn't screaming that to us. In fact, it's kind of disguising it. And we only notice this if we have a look at how the values in the legend have changed. Because what we might expect if something has gone up is a lot more red, right? So if we're comparing these two, for example, but because of the changing values, we don't see that. So this is just one example of how the map, the decisions that the person making the map has made might affect the types of conclusions we draw. And when I'm talking about maps, I just want to make it clear, I'm talking about these visual representations of spatial data. So that's what I mean in this specific case when I say maps for the rest of the talk. So before I go and talk more about maps, I just wanted to say hello. So as John said, my name is Reka. I am a lecturer in quant methods based in the School of Social Sciences at University of Manchester. And I'm also a fellow of the Software Sustainability Institute. If you want to get in touch, a good way to do that is on Twitter. I'm not very good at emails. And also there's my website, rikadata.net. So if you wanted to, for example, follow along with the slides for today, they're available there as well. So everything I do, I try and put on there and collect. So if anyone's interested in this sort of thing, then do check out the website. In terms of the kind of topics I do for research, I do lots of data analysis and geographical information systems, so spatial data analysis. I'm really interested in data visualization, and my general domain is around crime, transport, policing, that sort of thing. I'm interested in, I put new in quotes, new forms of data, which means in the School of Social Sciences basically means that I don't love surveys. So if something's not a survey or an interview or focus group or that sort of thing, then I usually get more excited. And my main sort of language that I work in is R. So all of the code for everything I'm showing today is available on my GitHub, which you can reach through the website as well. But it is all in R, so you'll have to translate it over to Python. So what do I have to do with mapping? Well, I teach a module on crime mapping, which is just introduction to putting crime and criminal justice data on maps and how to analyze it in spatial data analysis, that sort of thing. Excitingly, we've got a textbook forthcoming at some point in the next 12 to 18 months. But if you're interested in the development of it, this is the website where you can see, this is the GitHub repository for that textbook. But currently it's very preliminary stage, so keep that in mind. So why do we care about maps? Why should we talk about maps? Well, much of human activity, and the social scientists care about human activity, happens somewhere, right? So we all have bodies that we move through place and time also, but here we're focusing on place. And so because of that, there's maps about pretty much everything. We see maps everywhere. This one I grabbed from the BBC website today, and it's coronavirus mapped. We've seen lots of maps on this topic, so we can have a look at where the virus is on the increase, decrease, what's going on in the world. Many of these maps are very useful. So this map is very useful as things begin to reopen and lockdown is over. So for those of us in Manchester, this is the optimal Manchester Brewery crawl. So my partner has applied the traveling salesman algorithm to all of the breweries with tap rooms in Manchester. If you're interested in this, there's the link here. So you can implement this when all the breweries are back up and open. But yeah, some maps, very useful. However, there are many bad maps out there, maps where somebody made some decision whereby it's not very useful to us. So for example, here is a piece about Obama's divided nation, and apparently somebody chose a color scheme that does not translate when printed in grayscale or black and white. of course, there's the obligatory XKCD for this. A lot of maps will often resemble population maps. So if you're mapping where something happens, often if you don't control for population, you are then also mapping where people exist, and people, where there are more people do the thing you're mapping, and so on. So this is another common flaw of maps that you might see. Sometimes bad maps are funny. So this is a map of what is it? So this is the amount of hogs in the United States, and each black dot represents 5,000 hogs. So you can start seeing, where there are hogs in the United States. But then you also get some funny comments saying there's an untapped infinite hog supply in the ocean, but also each state is lined with an impenetrable wall of swine, and everyone there is trapped. But also Canada and Mexico have been lost to these hogs already. So sometimes these bad maps are funny. Some people collect the bad maps or funny maps. So there's a Twitter account called Terrible Maps, which if you're interested, I recommend following. Some maps are funnier than others. Some are terrible/terribly funny maps. Here you have the top 12 states to live in. Anyway, if we are to map something that is not terrible, not terribly funny, but something that represents our message that we want to convey with our spatial data visualization, with our map, what are some key considerations that we need to keep in mind? First, we need to really narrow down what is the intended message, right? What is it that we want to communicate with this specific map? And also, how do different choices that we make, so different maps, types, colors, bandwidths for your bins, like the first map that we looked at, how do these convey this message? So what is our message? And the many options that we have, the many decisions that we need to make when building our maps, how do they affect how we can convey the message that we want to? These are the key things to think about when making maps that are interpretable and easy to understand for people. And there's two key fields that we can draw upon when trying to think about how these decisions affect the ways in which people will understand our message from our maps. One is the area of cartography, which is map making. And the other is this sort of growing area of research into data visualization. And I put non-spatial because it doesn't just have to be spatial data visualization. There's lots of research that has to do with data visualization of non-spatial data where the learnings are directly applicable to a spatial visualization. So these are the two key fields in which there's lots and lots of ongoing research that we can use to inform our map making and to understand how the decisions we make when creating maps might affect the kind of message that people take away when viewing these maps. So I have some examples, but what these fields try and do is kind of build an empirical understanding of how people perceive the different ways of visualizing. So these fields are involved with building up an evidence base to say, this is, when you make this decision, this is the effect on people's understanding of the message you're trying to communicate with that particular piece of visualization. So I've got some examples to illustrate that, and the first one's pie charts. Pie charts have this lore, this bad reputation. If you make a pie chart, you are the worst. And it's lots of back and forth arguments on the internet about pie charts, that sort of thing. But actually, there's been some empirical work looking at, okay, why do we hate pie charts? Are they genuinely the worst, or do they kind of add some value? So in this specific study, they looked at 4 different ways of visualization. So there's this kind of square pie chart, which I think you can reproduce with a waffle chart, for example. This loading bar, horizontal bar chart. The pie chart, the infamous, and then this donut chart, which is a pie chart, but with a hole in the middle, because apparently if you take a hole out of the middle of the pie chart, it's cool again, and you can use it. And what they did is they presented these visuals to a group of participants with some percentage of the visual shaded blue. And they asked people to estimate how much of that is shaded blue. And then essentially they just looked at how often people got it wrong. And they took the one that people were the best at estimating, which in this case is this square pie chart. So that's a reference. And then basically how wrong people were compared to that. So with this loading bar chart, people were pretty wrong. But with the pie chart and the donut chart, I mean, they were more wrong than the square chart, but less wrong, slightly with a bit of overlap, than the sort of horizontal loading bar. So that's some empirical evidence supporting the pie chart a little bit over some visualizations, but not so much over others. There's another example. So people who are into data visualization, they might have heard of Edward Tufte. He's got this beautiful book called The Visual Display of Quantitative Information, and he's written lots and lots about how to visualize data. And one of his principles is this sort of data ink ratio, where you want beautiful minimalist graphs. So every bit of ink on your canvas should convey information, and anything beyond that just shouldn't be there. And he calls this extra fluff around charts, he calls that chart junk. So here there's two charts, they convey the same information. The bottom one, this minimalist one, is very sort of Tuftean, whereas the top one, it has lots and lots of chart junk. And then what these researchers did in this paper is compare people's perception and understanding of the message conveyed by these two different visualizations, and found that while I think it was relatively similar understanding, maybe a bit better understanding from the Tuftean one, recall, the extent to which people remembered what was being visualized a week later, or whenever the follow-up was much better with the chart junk chart. So there's a bit of back and forth there as well. And then, of course, there's lots of examples in cartography specifically to maps and how people read maps and understand maps. And there's vast resources and studies of color, on shapes, on everything. So there's lots and lots there. And it goes back sort of decades and decades. So for example, there's this one from 1971 where they were looking at graduated symbols on maps to represent information instead of shading, for example. And that's what we saw on the sort of BBC map of COVID across the world, right? And here we see they've been sort of experimenting and looking at what's better, circle size or a bar chart, and so on. So there's all of these neat bits of research that exist out there about what's what in trying to convey your message with a visualization. So within that massive field, I'm focusing now on addressing one specific problem, which is variation in the size and shape of areas that we're mapping, right? So these geographic areas that we might be interested in comparing between, for example. So one example, you've got these states in the US, you've got some very large states, so you've got massive Texas here, and then you've got some very small states on the East Coast, right? And so if we're looking at this, even though the size of the object, the size of the polygon doesn't really make a difference, it doesn't tell us any information except how much land there is there, it starts to kind of skew the eye. And it's the same in the UK as well, if we are looking at mapping local authorities. If we look at Scotland, for example, there's pretty massive local authorities. And if you look at London, you can't even really see the local authorities in London. It just becomes blurred by all the little boundaries. So this is a known problem. And the main issue is that the message that you're trying to convey is often obscured. So here, if I'm trying to visualize something by shading the different local authorities, you can't even really see what colors are happening in London. And this is not because of any visualization decision or not because of any artifact of the data. It's just because of the size and the shape of these individual polygons. So one thing you can do, fix this, is to distort the polygons. And there's lots and lots and lots of ways to do this. This is a paper sort of checking the state of the art of cartograms. which are ways of distorting the size of the size and shape of the polygon based on some sort of variable. And they might be a bit too small to see, but I just wanted to show how many there are because I couldn't even fit them all in one slide. They continue on to the next slide as well. So the idea behind these is that you use some other variable to weight the size and shape of that polygon. You might have seen those world maps where Canada kind of shrinks down to a very, very small line because there's very low population. That's the kind of thing that a cartogram would produce. This kind of transformation would produce. So, okay, this is interesting and this might be something useful, but do we know how does this transformation actually affect people's perception of the data that we're trying to communicate with our visualization? And that is the paper that I am going to show you some results from. So we had exactly this problem mapping local authorities in England. And what we were looking at in this case, we used data from the EU referendum results. And we were trying to show that, look, there was really this concentration of voting to remain in London. But when we produce this map, it just becomes very difficult to see this. You can see, okay, yeah, there's a bit of yellow there, but it doesn't come out as this obvious sort of hotspot or region where actually there was a very high percentage of people voting to remain in this, I don't want to say island, but in this specific bubble, say. So we come up with this map and it sort of communicates that message, but we just wonder, is there some better way to make this message seen? And we considered specifically 4 types of distortions. And so I'll go through what those were. But we considered 4 ways of augmenting these shapes of the local authorities in order to try and better communicate this method. And the types were to use a balanced cartogram. So that's where you weight the polygon by some variable to make the sizes more uniform, or depending on what you want to show. And also 3 different types of transformation into these sort of regular shapes. So we used the hexagram, and also we used a regular grid and hex binning of, or creating this hex grid, sorry, of the local authorities as well. And so while at first glance you might say, oh, I'm just going to change them to hexagons, actually how you do that, so depending on the decisions behind how you transform your local authority to hexagons, you might get different outcomes. So if you look at B and D, they actually look quite different, even though the shape into which we transform our local authorities is the same. So we created these 4 types of distortions, and I'll just go through how we did that. So the first distortion that we used is this balanced cartogram. So the balanced cartogram is slightly different than the cartograms that I showed on the other 2 slides in that we don't actually use a variable from the data set to change the size and shape, because there's a chance that that variable itself is also skewed. So population might be something that's quite skewed, right? So it might really blow up London and then just invert the problem, right? So we have a massive London and then tiny Scotland or something like this, right? So because our aim isn't to represent population size, it's to get this sort of balanced view of the local authorities. What we do instead is to scale by a minimum value. And this minimum value is basically the smallest that a polygon can be for us to be able to see it and to understand what is the data being visualized in it. So to be able to see what the content is inside, basically. And we use this to balance between the invisibility of the tiny local authorities and the distortion. So how we want to keep the map as recognizable as possible. So this is just for the curious. For example, let's say our sort of smallest interpretable unit, that's this minimum value. If that is 0.02 inches on this 5-inch map, then we can use that to weight the size of our polygons. And then, so we calculate those here. We create this scale by variable. And then we use that scale by to create a cartogram instead of, let's say, population size. So that's the balanced cartogram. And when we use that, we get this map output. So we can see that it's not done anything like blow up London and minimize everything else in terms of skewing by population or something like that, but it's kind of made everything a little bit more uniform, and it's still more or less recognizable that this represents England. The second transformation that we considered is the hexagram. So this is the same idea with as the balanced cartogram, that again we use a minimum value, but this time the minimum value is what allows each area, so in this case each local authority, to be represented as its own hexagon. So what we did in this particular case is we actually, instead of transforming, we used hexagonal binning. So we took the centroids of these polygons, and then we wanted to sort of bin them, so put them into hexagons. And we wanted to make sure that each hexagon contains only one centroid, so that each hexagon represents one local authority. And so what that looks like here, we took this, so the script here, all of this is from this paper by Richard Harris. So we take that script, which applies this transformation using the F multivar packages hex binning functions. And one decision that we had to make in this case is how many hexagons to have. And in that case, if you follow this, there's a chart in there that helps you choose. But because the example also uses local authorities in England, we also had a handy guide of, yes, the chart looks good on that, but also this is verified by the person who wrote this, so that's very good. So that's hexagrams, and that produced this map. So one sort of feature of this way of binning into hexagrams is that they do not necessarily have to all tessellate. It doesn't have to be a perfect sort of tile mesh of hexagons. Instead, they might be located basically wherever the centroid of the local authority deems it best to be put. So that's slightly different than the next one, which I will show in a moment. So the third transformation is creating a square grid. So for this, we use the GeoGrid package, which is from Joseph Bailey, and you can click on the link to see the details behind that specific package. But basically, the main aim of GeoGrid is to try as close as possible to preserve the original geography. So it wants to be as true to the original shapes as it can possibly be. And in order to do this and to use this grid, there's two steps that we take. First, essentially what it does is it generates a random grid, or it generates a grid that tries to match this geography using a random seed, or using a seed to randomize from. And the sort of notes in the package are to use a variety of seeds and then see which one of the grids looks good. And then once you've found a grid that you think looks, this represents most accurately my original geography, then you take that grid and then you assign from the original geography the attributes. So you basically assign one local authority to one grid. And you use something called the Hungarian algorithm in order to kind of minimize the distance between the centroid, the distance between the centroid of the local authority and the of the grid in overall. So these are the two steps. We basically calculate this grid, and you can run this over and over and over again until you get a grid that you're happy with. And then when you are happy with that grid, then you assign the polygons to that grid. Now, what we found is that it didn't actually vary a lot at all for us. In the example, I think they use London, and there's some similar ones, and then there's one that's outstandingly better, I think. But actually, for us, there was no noticeable difference in the different grids. So that's one thing we noted. And then and then this is what that resulted in. So it's slightly different, right, than we were originally expecting. But here is our GeoGrid version of England. And then to do the same for the hexagons, it is the exact same process, except instead of a square grid, it's a hexagonal grid. Right. So again, we create this grid, we find our optimal grid. Again, they pretty much all look the same. And then we assign the polygons. And that looked like this. And here you can see it is really following this perfect tiling with one or two holes, I guess. But it's really just trying to have the shape that you gave it in this tessellating hexagon form. So these were the 4 images. I'll just show them once more side by side to tell you what we did. So these were the 4 images that we've created. And keep in mind that all of these are using the exact same data, right? So they're all visualizing the exact same data set. But what we wanted to know is, how does visualizing our data in these different ways affect people's perception? And so to measure this, we created a survey, and we said, okay, this is the statement that we think best represents our map. And the statement is, high values in yellow appear to be clustered near one another with a handful of outliers elsewhere in the country, right? So we basically wanted to say people who voted Remain seem to cluster in London with a couple of spots here and there. We didn't include what the visualization was, because if people were familiar with the results, they might have already known, oh yeah, London had a big cluster of people voting to remain in the EU. So we took that out and we just said high values in yellow. And we wanted to ask people how much they agreed or disagreed with this statement. This statement we thought represented our data, and this is the message we're trying to convey. So we had this 5-point Likert scale from strongly agree to strongly disagree. And then we presented people with these maps. So higher agreement basically means that the map better represents this statement that we think is the sort of message of our data. And we showed this map to a bunch of people on the internet. We were not taking representative sample. We went convenience sampling. We used Twitter, we used Reddit, whatever. But we had 768 respondents rate these maps. These were the people who rated all of the maps. And so results are in. What we wanted to see is how much people agree or disagree with that statement in each of the maps we've created. So here's our original map, this top one. And you can see, okay, about half, just under half people strongly agree with the statement that we're trying to convey. And then this big sort of light green chunk also is slightly agree. So we get quite a lot of agreement with the original, a bit of disagreement, but not that much. But when we use the cartogram, the balanced cartogram, we get a lot more agreement and a lot less disagreement. Same with the hexagram, it's slightly less agreement than the cartogram, but more than our original. However, if we're looking at the 2 implementations of the GeoGrid, the square and the hexagons, then we get a lot of disagreement and really not that much strength in strongly agreeing with our results. And for good measure, we wanted to sort of quantify the extent to which people agree or disagree with each map. So we used the original map with the local authorities sort of untouched as our reference, and compared people's agreement versus disagreement in all of the other maps to that to the original local authority map. Just dichotomizing agree together and disagree together. And we found again that people are much more likely to be agreeing with our statement that we think the message should be that people take away from that map in the cartogram and the hexagram versions, whereas the 2 GeoGrid versions, they are actually much more likely to disagree with the statement than our original map. So this was very interesting because we could have just gone with any one of these transformations, but clearly our decisions have an effect on what our readers take away from these maps. So for conclusions to take away, we said that these methods to visualize the geographic information, they can be more accurate, or they can make people more strongly agree with the message we're trying to communicate in certain instances, but then in other instances, actually, they might have the opposite effect. And so it's very important to choose the method with consideration, and to really think about what is the question, what is the message that we want to communicate, and how can we best communicate with that, and how might we be accidentally uncommunicating that, or misleading people just by choosing a different way of visualizing our data. So that's all I had. The paper, if anyone's interested, is online, and you can reach it through that link. These slides are available as well on my website. If you have any questions, you can ask now. You can message later on Twitter. You can get in touch. My email's on the website as well. Or Sam Langton, who's the first author on this, is his work as well. Do feel free to ask questions. In fact, if you ask me a difficult one, I'd probably just push it onto him. So thank you very much, and I hope that was interesting.
Thanks, Rika. It really was a bit of a twist at the end. I was kind of thinking you're going to be comparing it along to what the absolute values of the absolute results were. When you're saying people thought that yellow areas were higher levels of concentration, and but actually they were wrong. But I guess your point stands very well made, that there often isn't a kind of binary answer to analysis you do when you're looking at real world situations. It's about understanding with the broader context.
For sure. And often you might accidentally be misleading people by saying, or you might be misleading yourself, even if you're looking for a concentration and you choose the wrong way to visualize your data. And then you say, oh, looks like there wasn't really much of a much of a pattern there at all. But if you chose the different one, you'd say, wow, there really was. And so in this case, we knew from previous spatial data analysis as well that, okay, yes, that is a true concentration of values there. But then based on the different ways we visualized it, whether we succeeded or failed to communicate that to our audience, it really depended on, not just whether or not how wrong they were, but actually what we did if we were comparing it to just leaving it alone, right? Not transforming anything. We're just, here's what a local authority looks like. Here you go. People seem to get a pretty good understanding that, okay, yeah, I agree with this statement. But then compared to understanding from the basic one, once we made the transformation that we thought would be helpful, in 2 cases, yes, it was. But in 2 cases, actually, no, it made it worse. You should have just not touched it.
Yeah, I mean, you kind of touched on the comparison between the EU referendum and the presidential campaign from 2016. I mean, there's a lot of graphs I saw at the time going around on various social media with lots of people complaining that, oh, there's a lot of people who, I mean, yeah, the vast majority of Americans voted for Trump and wanting Trump because an awful lot of, states' electoral college representations are predominantly red, which, as you mentioned, describes the area rather than the population. And kind of it sounds like the conclusions from your from your research has been this is all about narrative, rather than, and there's a distinction between doing the actual measurement and understanding and then conveying the narrative in a manner that people understand. Is it all completely contextual in conveying the results that you want, like the Georgian healthcare department?
Yeah, I mean, it's that basics, how to lie with statistics, or how to lie with charts, how to lie with maps. It might be that actually you're truly representing the data, so you're not actually doctoring your data at all, but it's how you visualize it. That means that people will draw completely different conclusions. I mean, the election in the US is another interesting one because they have this thing called gerrymandering, where they redraw electoral boundaries to make sure that the majorities will, benefit the person in power at the time, so they get reelected and so on. So there, it's not only they're not only redrawing the visualization and sort of lying, but they're also creating the data and the results that they want by redrawing the actual area. So that's a whole new tier of this.
Yeah, I can't imagine there were many sound methodological ways of getting around that kind of discrepancies in the real world.
No, I'm not sure. I think there are many smart people working on this. So
just going back to kind of some of the stuff you were doing around the pie charts visualizations, did I read correctly that the waffle chart had an absolute error of 0 or close to 0?
yeah, I think again that was. It's been a while since I read that paper, but I think what happened was they took that as the best scoring visualization and then compared to that how much more wrong people were.
Okay, that makes sense.
I think, but sometimes, so thinking of waffle charts, sometimes you have them kind of gridded up as well, and then you can actually just count the squares. So in that case, I can understand an error of 0, although I don't know, maybe they had a very good participant base. But I'd need to reread the paper, but from my recall, they just used that and compared against that as, okay, is this better or worse than?
Okay, I mean, from that, assuming your explanation is true, which it makes perfect sense. From what I understand, the criticism of the pie chart is that it's hard to estimate the value based on the area of a chart that's shaded. When I was looking at it, I felt more confident estimating with the pie chart than I did the waffle chart. Do you know why people were more accurate with the waffle chart?
Oh, I don't. I don't know if there's that kind of qualitative follow-up. Maybe the grid system. I mean, the thing with pie charts is it's really fun to hate on them, but if you have 2 values, they seem to be pretty decent, right? We're not that bad at it. I think the problem is we're not good at circles as humans. We're better with straight lines. And so I think the idea is that you shouldn't use it in cases where you have sort of lots of values, right? So let's say I have a categorical variable with 20 different outcomes. That will probably make it quite noisy and difficult to read. But with 2, I think it seems to be okay based on this kind of evidence. Now, if you make it 3-dimensional, I think that's problematic for sure, because you're introducing non-angled. I don't even know what you're doing there, but for 2-dimensional with just 2 values, I think they're fine.
Okay, that makes sense. So, are there any kind of special considerations you'd think about when working with spatial data compared to regular data?
So I think there's this kind of rule of spatial data or law, Toller's law, that like everything is related to everything, but near things are more related to each other than far away things are. And that's why when you're carrying out spatial data analysis, you have to sort of account for that there's the nearness is a value, right? That's something that's important that we need to think about. And so with spatial data visualization as well, you might find, oh, look, there's this hub here or hotspot here or something like that, but it might not actually be anything about patterns in that data. It might just be that your near things are near each other. So that might be one thing. And also, I didn't talk about color in this presentation, but one thing that's very important for maps is choice of color, especially when we're considering accessibility. So if you think about people who are colorblind, and then you have a map where the high values are green and the low values are red. If you have this kind of red-green color blindness, then they look exactly the same. And so I showed that map of, what is it, Obama versus, I don't remember, but the map that printed black and white, and all the states had the exact same color. So these kinds of things, maybe that was probably a green and blue or green and red or something like that map. But that's what it would look like to someone who is colorblind to those. And also when you print black and white, that's what it looks like to everyone. So for that as well, because usually with something like a pie chart, you would have a boundary or something like that, or a line chart or histogram, you can see. Color is maybe not so important, but in maps, if you're using color, then yes.
Cool, good point. So do you think, in the context of nearness and people understanding their locality and their preconceptions, I suppose, do you think removing the local element makes readers struggle to understand how their locality voted?
What do you mean by removing local element?
This is a question from Anonymous, so I'm not
Oh.
sure. But I would think in the context of, so looking at when people vote, if you ask the question in a local election, this is a distribution. If you then take away a label saying it was a local thing. Yeah.
Okay, I'm not sure. I might be answering a completely unrelated question, and I'm sorry if I'm misunderstanding. But people's perception of their local area is usually very different than their perception of general trends. So we see this in crime research, for example, that if you ask people, the same people this question in the survey, you ask them, is crime in your neighborhood going up, going down, or staying the same? They usually say, oh, it's going down or it's staying the same. Yeah. But if you ask them, what is crime like, at a national level, like, oh, it's definitely going up. Yeah. It's not in my neighborhood. This is fine. But elsewhere, yeah, it's definitely going up. So people definitely, if we're talking about things where we're asking people to judge their local area versus judge what's going on in patterns generally, you do see that quite a lot. I'm trying to think how else I could answer the question.
I mean, is that to do with is that a crime specific thing? Because obviously crime can be a very politicized issue, or is it just that kind of trend or inaccuracy hold across other areas?
I'm not sure, but I would assume. Sorry?
I ask you as a crime expert.
Yeah, it definitely. I would be surprised if it didn't. I think people tend to estimate bad things going on around them a lot more, sort of elsewhere, but rather than see the immediate impact. I know that for fear of crime, for example, depending on how you measure it. So this is now not depending on how you visualize, but how you measure. Depending on how you ask the question, what you specifically tap into, you get very different answers. So if you ask this general, in the past 12 months, how worried have you been about crime? It's a very hard question to answer. The past 12 months, I don't know, so much has happened. I guess, I'm this age, this gender, I live in this neighborhood, I'm pretty worried. Yeah, let's say I'm worried sometimes. Yes, a little bit worried, whatever. But if you ask people in the past 24 hours, or how frequently have you worried about crime in the past 3 weeks or something like this, or actually get them to report when they feel safe and unsafe, you see people are most of the time do not care about crime at all. And then more recently I've started, so I used to, or I still kind of do research into perception of crime and where people feel safe and unsafe. And now I'm transitioning to looking at perception of COVID and where people feel safe and unsafe and that sort of thing. And we're finding pretty much the exact same patterns. If you ask generally, like, oh yeah, I'm super worried, I think this is super scary. But then you ask, how often did you worry in the last 3 weeks? And they're like once or twice. I wash my hands. So I would be surprised if this was only for crime trends that people thought this way.
Oh, that's fascinating. Thank you. So it's a good question from Anonymous. What's the relationship between how we represent space, our land area, and a map, and how we bin the data?
That is a very big question, because there's a lot of, so one of the things that I always look at when I look at a hexagon map. So these ones, when I showed these hexagon maps, it's transforming a local authority into a hexagon. So that shouldn't be too, like, shouldn't increase, or it shouldn't make the results too weird. But one thing that happens is this binning, right? So hex binning, for example. So let's say you have point level data, you have crimes or whatever, and then you overlay a grid of hexagons. Depending on where those are, right, they might create hotspots where there aren't any, or they might divide up hotspots where there might be some. So that choice of how that grid gets overlaid is actually very, very important. And there's lots of different considerations to take into account when dividing data into neighborhoods. So one of the things is where your neighborhood ends. On the local authority, on the map of local authorities, there's this solid line, right?
New
Whereas
studies
actually
available on
that might
Prolific.
not be something that's reflected in the geography of the place. It might be that you're gonna, if you have a crime on one side of it, and then you have an offender that lives sort of on the line or something, they will travel in one direction and offend, and in the other direction and offend as well. So that's a very important question, and something that there isn't like an answer or that I can give. Well, this is if once you chop your point data into these hexagons, then that's it. That hexagon is a sacred unit of analysis, and it's going to tell you these things. I think it's about thinking about your unit of analysis, and should you be binning things, and when you are binning things, think about how that might create artificial boundaries as well.
Cool, thank you. Good answer. Very, very big question.
Yeah.
So are there any studies on different kinds of maps showing the same information visualized in more traditional non-map ways? So, I mean, comparing a scatter plot or a box plot to kind of a map-based visualization system.
Yes, yes, for sure. And one of the big things in spatial data visualization, I started off with like everything we do happens in space and so on, is just because it has coordinates does not mean that you have to put it on a map. And a lot of the times there are much better alternatives. So there's a really neat paper that came out of Vancouver, Canada, where they were looking at different ways of mapping crime along street network. And so, for example, if you have your map, right? So we have a map, and here's North America, you've got your grid system, right? And then you've got your route that's like at this busy avenue, and you can map the hotspots for the different blocks. So you can see here it's like very dark red, and then a bit yellow, and then green, right? And you have this map, and that's okay. But let's say what we wanted to compare multiple years, right, of this, how has the hotspot moved up and down this avenue? Let's say we opened a shopping mall there or something. And then all of a sudden you have to have side by side like 3 different maps for 3 different years, and you're kind of eyeballing it like this is a different hue of orange than that year. And so what they did is they actually took the street as the x-axis of a chart, and they took the intersections as the axis ticks, and then they had number of crimes as your y-axis, and then each year was a line chart. So you could see like, okay, so this year, this intersection had a lot of crime, and then this one went down. Oh no, it's the same intersection this year as well, but this year this intersection went down and it shifted further along the route because we did something. So actually they turned this map, which you have to sort of look at 3 side-by-side graphs, to overlaying 3 line charts of crime along the street network over time, each line being a different year of crime data. And that was a much better visualization. And then they called it street profile analysis. So if you want to search the paper, I think it's called Street Profile Analysis by Valerie Spicer and colleagues. That's a case where definitely it did not need to be on a map.
Keeping it, going with Tufte's axiom of keeping it simple.
Exactly. Yes.
Cool. I think that's all the questions we've got. So Rika, thank you very much for joining us and discussing maps.
Thanks for having me.
Cool. Well, thank you to both of our speakers. Thank you as well to all of you for joining us. And just before we go, I'd like to say thank you to our sponsors, Horsefly Analytics, Cathcart Associates, and of course NumFocus, who always you kind of help make PyData both the events and a lot of the tooling available to everyone. We'll try and be around in the Slack afterwards if you want to have a chat or you want to ask any questions. But thank you very much for joining us. And hopefully we'll see you again at the, I just remembered, Python Northwest and Herplus Data are having their August event on 20th of August. It'll be jointly hosted with Python Northwest and Herplus Data, both wonderful groups, and it'll be great. So you should definitely go along to that. But yes, thank you for joining us. Hopefully see you next time.